Hello everyone. Today I am here to discuss the zero and first order reaction. After studying this lecture, you shall be able to know about the concept of rate law, understand the concept of order and molecularity, know the concept why high molecularity reactions are rare, and understand the integrated equations of zero and first order. So let us discuss what is rate law. The rate of a reaction is directly proportional to the reactant concentration, each concentration being raised to some power. For a substance A undergoing reaction, that is, rate is directly proportional to the concentration of A having a power n. Rate is equals to K concentration of A having a power n. This is first equation. For a reaction, that is 2A plus B gives product, the reaction rate with respect to A or B is determined by varying the concentration of one of the reactant, keeping that of the other constant. Thus, the rate of the reaction may be expressed as rate is equals to K concentration of A having a power m, concentration of B having a power n. This is the second equation. Expressions such as first and second tell the relationship between the rate of reaction and reactant concentration. So, an expression which shows how the reaction rate is related to the concentration is called rate law or rate equation. The power of the concentration N or M in the rate law is usually a small whole number integer 1, 2, 3 or fractional. The proportionality constant K is called rate constant for the reaction. What is the characteristics of the N? N may be the integer and it may be a fraction. The order of the reaction do not have any relation with the stoichiometry of chemical reaction. Order of reaction only we find out by experiment. Now we discuss the units of rate law. Rate is directly proportional to the concentration term of A and concentration term of B having a power x and y. When we introduce a proportionality constant, then the rate is equals to K bracket में A and B having a power x and y. So when we calculate the unit of K, then it will be written as K is equals to R divided by A and B having a power x and y. Rate, which is equals to concentration divided by time. So concentration can be expressed in terms of mole per liter and time it should be represented by time. For the concentration terms A and B having a power x and y, which can be represented by or expressed by mole per liter and power should be added. Now, when we calculate that, mole per liter time inverse multiply by 1 upon mole per liter and the powers should be expressed by the term N. So, K is equals to mole divided by liter 1 minus N time inverse. This is the unit of the rate law. The unit of the rate constant depends upon the order of the reaction. So by this unit of the K, we calculate the order of the reactions. Either it should be 0, 1 or 2. So for zero order reaction, when n is equals to 0, we put the value of n and calculate the unit of the zero order reaction. We know very well K is equals to mole per inverse 1 minus n time inverse. So we put the order of the reaction means 0 in place of n and then we get mole per liter time inverse. This is the unit of zero order reaction. Similarly, for the first order reaction, the unit of K is mole per liter 1 minus N time inverse. So in place of N, we put the value of 1 because we calculate for the first order reaction. So we get time inverse. For second order reaction, we put the value 2 in place of N, then we get mole per liter inverse time inverse. What is the order of reaction? The order of reaction is defined as the sum of powers of concentration in rate law. Let us consider an example of reaction which has a rate law. So rate is equals to K, concentration of A and concentration of B having the power M and N. This is the first reaction. The order of such reaction is M plus N. The order of the reaction can also be defined with respect to the single reactant. Thus, the reaction order with respect to A is M and with respect to B is N. So, the overall order of the reaction is M plus N, may be the range from 1 to 3 and can be frictional. These are the some of the examples how to calculate the order. In first reaction, rate is equals to K, concentration term of N2O5. There is only one power, so the order of reaction is 1. In the second equation, rate is equals to K, the concentration term H2 and I2 having the power 1. So sum of the powers, that is 1 plus 1 is equals to 2. So this is the order of the reaction. For the third equation, the power is 2, so the order of reaction is 2. And in the last equation, rate equals to K, H2 having a power 1, NO having the power 2. So if we sum these two powers, 1 plus 2, the order of reaction is 3. So this is the way to calculate the order of the reaction. So reaction may be classified according to the order. If in the rate law, first our M plus N is equals to 1 means it is a first order reaction. If M plus N is equals to 2, it is second order reaction, and M plus N is equals to 3, it is third order reaction. Now we will discuss molecularity of the reaction. The number of reacting species like atom, molecule and ion participating in elementary reactions means which is obtained in the single step or also called as non-complex chemical reactions which must collide simultaneously is called molecularity. For example, the number of reactant molecules involved in the reaction, that is unimolecular, means only one of the reactant participate in the reaction, that is called unimolecular. So we give the example, malic acid convert into fumaric acid. Why it is called bimolecular? Because two reactants are responsible for the formation of product. Trimolecular means three reactants are participating in this reaction. Why high molecularity reactions are rare? Most of the reactions involve 1, 2 or at the most 3 molecules. The reaction involving 4 or more molecules are very rare. The rarity of the reaction with high molecularity can be explained on the basis of kinetic molecular theory. According to this theory, the rate of chemical reaction is proportional to the number of collisions taking place between the reacting molecules. The chances of simultaneous collision of the reacting molecules will go on decreasing with increasing in the number of molecules. Thus, the possibility of the three molecules colliding together is much lesser in case of bimolecular collision. For a reaction of molecularity 4, the 4 molecule must come collide and collide with one another at the same time. So the possibility of their doing so much less than even in the case of trimolecular reactions. Hence, the reactions involving many molecules proceed through a series of the steps, each involving two or three or less number of molecules. Such reaction is called complex reactions. At the slowest step determines overall rate of the reaction. Now, how to calculate the molecularity of the reaction? Let us discuss with simple examples. That is, 2NO plus O2 gives 2NO2. The stoichiometry of NO is 2 and the oxygen is 1. So, if we sum this stoichiometry of the reactant called molecularity. So, 2 plus 1 is equals to 3. So, the molecularity of this reaction is 3. In the another example, H2 plus half O2 gives H2O. When we multiply the whole reaction with 2, then the stoichiometry of hydrogen is 2 and oxygen is 1. So 2 plus 1 is equals to 3. So the molecularity of this reaction is 3. Now let us discuss the difference between order of the reaction and molecularity of the reaction. Order, it is the sum of the powers of the concentration terms in the range of rate law expression. Molecularity, it is the number of reacting species undergoing simultaneous collision in the elementary or simple reaction. Order, it is an experimentally determined value, whereas molecularity is the theoretical concept. Order, it can have fractional value, whereas molecularity always a whole number. Order, it can assume zero value, whereas molecularity cannot have a zero value. Let us discuss zero order reaction. For zero order reaction, the rate of the reaction is independent of the concentration of reactant. It means the rate of reaction remains same irrespective of the concentration of reactants. For example, CO plus NO2 gives CO2 plus NO. Consider a reaction when the reactant is converted into product. Then the differential rate expression for zero order reaction is rate equals to minus d upon dt multiplied by r is equals to k, or minus dr concentration term is equals to k dt. When we integrate these equations, then integration of dr having a limit r0 rt is equals to k integration having a limit 0 to t dt. When we solve this integration, we get k is equals to r0 minus rt divided by t. Now calculate the half-life period of zero order reaction, that is T half. So when T is equals to T half, then RT is equals to R0 by 2. So put the values of T and RT in place of RT half and R0 by 2. So T half is equals to R0 minus R0 by 2 divided by K. Now we solve this reaction, we get T half is equals to R0 by 2K. Hence, the half-life period of zero order reaction is directly proportional to the initial concentration of reactant. So there is some example of zero order reaction, that photochemical combination of H2 and Cl2 and decomposition of ammonia over molybdenum and tungsten sulfates. Now we will discuss the first order reaction. Consider the reaction. The reactant is converted into the product. Let us the initial concentration of the reactant is equals to R0 at time t is equals to 0, and the concentration of reactant at any time t is equals to RT. So the differential rate expression of the first order reaction is rate is equals to minus d upon dt, R is equals to kr. So minus dr divided by r is equals to k dt. So we integrate the above equation gives integration having a limit r0 to rt dr by r is equals to k integration having the limit 0 to t dt. So when we solve this integration, we get minus ln rt upon r0 equals to kt, and kt is equals to ln r0 upon rt divided by whole t. K is equals to ln r0 by rt divided by t. When we convert ln into the normal log, then we can say k is equals to 2.303 divided by t log r0 upon rt. As k is equals to ln r0 upon divided by rt divided by t, so ln rt by r0 is equals to minus kt. When we convert in exponential term, then we can say RT by R0 is equals to E minus KT, or RT is equals to R0 exponential term E minus KT. So from the above equation, it is obvious that the concentration of reactant molecules falls off exponentially. Now we discuss the half-life period of first order reaction. The half-life period of the reaction can be defined as the time required when the half of the reactant is converted into product, or it can also be defined as time required for the reaction to be half completed. So when T is equals to T half and RT is equals to R0 by 2, as we know T is equals to 2.303 divided by K dot log R0 upon RT. So we put the value of T, that is T half, and RT, that is R0 by 2 in this equation. So T half is equals to 2.303 divided by K dot log R0 divided by R0 by 2, or T half is equals to 2.303 K dot log 2, or T half is equals to 0.693 divided by K. Means for first order reaction, the half-life period is independent of the initial concentration of the reactant. These are some examples of the first order reaction in which the thermal decomposition of nitrogen pentoxide in the gaseous phase, N2O5 in gaseous phase, it decomposes into N2O4 plus half O2. Acid catalyzed hydrolysis of ester in presence of large concentration of water, means acid COOC2H5 plus water is converted into CaCCOOH plus C2H5OH, and the inversion of the cane sugar in presence of dilute mineral acids like C12H22O11 plus water gives C6H12O6 plus C6H12O6. So these are the examples of the first order reaction. On the basis of the presentation, these are some practice questions like define the term rate law, discuss the units of rate law of zero, first and second order reaction, explain the difference of order and molecularity, discuss the integration equation of zero order reaction, prove that first order reaction the half-life period is independent of the initial concentration of the reactant, and discuss the integration equation of first order reaction. These are the references. Thank you.